In this session, we will see how model-based design makes the motor control faster and easier. Welcome in today's webinar about motor control with Simulink and model-based design, which is the third and final part of the Power Electronics Control Design webinar series. My name is Ákos Pallag. I work as an application engineer at Gamox Laboratory Solutions. Today, I'm going to talk about how we can develop our motor control using Simulink and model-based design. Let us start with an overview about motor control in general. In our previous webinar sessions, we saw how our power source, battery, is modeled and controlled in order to supply the electricity and how to convert this electricity from one form to another that can be used by the load. In this session, we'll focus on how to use this electricity by an electric motor, how to model the physical plant and design our control algorithm. Brushless motors are everywhere. We can find them in electric vehicles, trains, industrial drives, medical devices, and even electric longboards. Contrary to brushed motors, they have high efficiency, requires low maintenance, but in the meantime, they demand complex controls. These kinds of motor control algorithms like field-oriented control regulate speed, torque, and other performance characteristics. So by using field-oriented control, we can digitally control these electric motors. Here are some points highlighting the most typical challenges for motor control engineers face nowadays. One thing is that we need to start design work before motor hardware became available. Even when the hardware is available, it's essential to quickly go from design to implementation and to test on the hardware. Another aspect is that we need to test the software to certify with specific standards. The last challenge here is because of the complex motor control algorithms running at high sample rates, it's difficult to implement the control algorithms within a short amount of time. Simulink and model-based design can help and accelerate our workflow for developing embedded motor control algorithms. We can quickly put together a control system and start testing and verifying it in closed-loop desktop simulation. This can be done even before the motor hardware is available. What we provide is not only quickly go from design to implementation by automatically generating code from the Simulink model, but also using this code to spin the motor. And to minimize development time, we have many of reference examples to quickly get started for our next motor control project. Most importantly, the reason why one would choose to use Simulink is faster development time. Here's one user story for this related to Bosch. Bosch engineers had a little more than a year to design, to implement, test, and prepare the e-bike system for demonstration at the Eurobike trade show. Because they were building an entirely new system, the team needed a way to simulate their controller design and then quickly deploy it to an embedded microcontroller or prototyping hardware for testing on an actual bike. Bosch engineers used model-based design to develop the e-bike drive system, which was completed in accordance with the company's functional safety standards. Thanks for Simulink, Stateflow, and the add-on tools for controller and plant modeling, for verification, for real-time testing, and code generation, they developed the control system that met with the crucial market deadline. In release 2020A, the motor control block set was introduced, and then in 2020B release, it was equipped with a major upgrade that will automate and simplify the development process for embedded motor control algorithms. The product provides pre-built algorithmic blocks optimized for generating efficient code. And on top of that, we also provide blocks for sensor decoding, flux observers for sensorless control, motor parameter estimation, automated loop tuning, and further reference examples. In this session, we will see how model-based design makes the motor control faster and easier. Let us move on and see how can we design our motor control algorithm with Simulink and model-based design. As it was mentioned, brushless motors require complex algorithms like field-oriented control. So let's take an example of a permanent magnet synchronous motor with field-oriented control on which we can demonstrate our workflow. As we can see from this overview of system-level block diagrams, we differentiate the control algorithm and the physical system by colors. On the physical system side, we have the voltage supply that could be represented with a battery block, for example, an inverter, and our PMSM motor. From the control side, there are many components such as Park and Clarke transforms to convert currents and voltages between stationary reference frame and synchronous reference frames. On the outer loop, we have speed controller and inner loop current controller. To do closed loop control, we also have position and speed feedback from either sensor decoding logic or flux observers or sliding mode observers for those of you who are interested in sensorless control. Let's see how to develop and implement field-oriented control with Simulink. To give a structure to start with, we will use this very simplified workflow covered by these key steps. In the example models, a ADC C2000 motor control kit is used to illustrate the workflow. The kit includes a surface-mount motor, F28 series microcontroller, and a three-phase inverter. The first step of our workflow is to calibrate our sensors. We will start the sensor calibration by measuring phase currents using ADC. Calibrating current offsets is essential to ensure accurate current measurement. With the motor control block set, we provide a reference example for ADC offset calibration. The reference example includes a model that we can generate code, we can download it to the processor, and then a host model that will control the target. As we can see here, we start with disconnecting the motor from the inverter to make sure there are no phase currents going through the motor. So the model we generate code from captures the ADC counts and send them over through serial ports to a host model. Next, we can run this host model and use a scope to read the current offset. By reading the mean values of the signals, the offsets of phase A and phase B currents are determined. And finally, we can enter these offsets into MATLAB script so that we will use them later for closed loop control. Let's see how it works in the practice. So as we can see here for ADC offset calibration, we disconnect the motor from the inverter. Motor control block set provides a reference example for spinning the motor with open loop control. We can also use this example to calibrate the ADC offset. So as we see, the model we generate code from to run on the processor captures the ADC counts and sends them over serial to a host model. So we have this model, and we can generate C code and deploying it on the controller. Once it is done, we can also run a host model and start the calibration process. So we click on run, and we can start the calibration by this switch. We can also use the scope to plot the ADC readings for phase A current and phase B current. We can look at the mean signal values, and this will show us the offset for phase A current and phase B current as well. So this way we have our ADC offset values, and we can use them later on in the process. Next, we will compute the position sensor offset. The kit that we provide can calibrate for both Hall sensor and quadrant encoder. Here we use a Hall sensor as an example. For those of you who are interested in sensorless field-oriented control, you could definitely skip this step. So we start with a model that we generate the code from. The idea is that the model runs open loop control to compute the position sensor offset. And basically, the Hall sensor offset takes reading until the position is commanded to be 0 degrees. So we generate code from this model and download it to our processor as previously. We then use a host model to start the calibration. After we click on the run button and start the calibration with the switch, we can see that the motor starts spinning and the offset value will be automatically computed. The green LED shows that the motor is spinning counterclockwise, which is the right direction. If not, and the motor spins clockwise direction, it would turn red. So this way, as we can see, we can compute the position sensor offset value that we can also use further on. The second step of our workflow is to estimate the parameters of our motor. As we know, an accurate plant model helps us better design for our controller in the closed loop simulation. In our case, we have an actual motor and we can take advantage of that. So with motor control block set, it also provides instrumented tests we can run on the processor to estimate the motor parameters. Another nice thing is that we also have a further host model to control and monitor the progress of parameter estimation. That's how this works. So we start with a host model, which serves as a user interface. Here we define a few parameters, nominal voltage, current, and speed, and the input DC bus voltage. We also define the Hall sensor offset based on our previous computed value. Once we have defined all the values, we go to a target model and update the values from the instrumented tests to generate the code. We then start this parameter estimation from the host model. The tests are run on the motor to estimate the stator resistance, the inductance on D and Q axis, also the back EMF constant, the moment of inertia, and the friction coefficient of our motor. Once it is done, we can also use provided scope to examine the signals of our interest, like speed in this case. And now that we have the estimated parameters, we can actually save them to a mat file for further use them in the physical plant parameterization. If we switch to MATLAB and if we load this file, we will see a structure with the estimated motor parameter values. One thing to be noticed is that parameter estimation supports not only Hall sensor and quadrant encoder, but also sensorless control, which means if it's not necessary for us to have additional sensors, we can also use this method to estimate motor parameters. So we have seen motor control block set parameter estimation capabilities, which are useful if we already have the motor hardware. However, sometimes we have to start development before the hardware is available, just like as we discussed earlier. In that case, we can also import motor parameters from a datasheet, parameterize our motor from finite element analysis tools such as JMag or ANSYS Maxwell, or from dyno data as well. There are examples and capabilities using Simscape Electrical, and other products can help you do that, like Powertrain block set for the dyno example. Now that we have our motor parameters, we can model the motor and inverter dynamics. At this point, let me switch to our example model. So in this reference model, also provided by motor control block set, from the physical part, we have three variants for modeling the motor and inverter. We can choose them by assuming what kind of fidelity level we want to use. In the first variant, we use blocks from motor control block set for modeling linear lump parameter motor dynamics with fixed inductance values, and by directly loading the estimated parameters into this block that we already computed from the previous steps of our workflow. Also, as for an inverter, we have an average value block, and it all serves and helps us speed up the simulation process. In the second variant, for those of you who are interested in switching events, in the power electronics, we can use Simscape electrical blocks. So we have here PMSM block for our motor model. We can also use the previously estimated parameters as well, but we have we can also add several more parameters to our models, and several physical phenomena can be shown during the simulation, the effects of it. So for our inverter, we can also use a block from Simscape Electrical. For a three-phase converter, we can definitely choose between also the fidelity levels. By default, we are modeling an ideal switch inverter, but we can also model power semiconductors such as IGBTs or MOSFETs for our inverter model. And for our third subsystem, it includes a modular multi-level controller for also using a different kind of inverter model combined by our PMSM Simscape electrical block. So as we can see, we have capabilities to model different level of fidelity, ranging from system level performance analysis to detailed electric motor drive design. Each task requires different physical effects to be captured in the motor model and in the motor simulation. We can model a linear lump parameter motor dynamics, just as we saw in the reference model. But in some applications, we will want to model the saturation and the spatial harmonics. We can do that with the use of Simscape Electrical. So system engineers often rely on more abstract motor modeling that balances mechanical and electrical power to accelerate motor simulation and analyze system-level performance of a motor drive. For rapid motor simulation, we can integrate tabulated loss information into a system design level motor model and check the behavior of our design as a part of a larger system, while still accurately predicting the overall system efficiency. No pulse width modulation or power electronic switching is included. We work with simplified dynamics to get a steady state equivalent for efficiency mapping. We can develop a proof of concept electric drive control strategy using the control design fidelity level. We can ensure realistic motor simulation behavior by estimating parameter values based on measured data. Motor drive designers may need to import finite element analysis data to optimize drive design parameters while minimizing the losses. To account for magnetic saturation or parameter variation under different load levels, we can incorporate finite element analysis data that describes a nonlinear flux current relationship in our motor model using the motor drive design fidelity level. The highest fidelity motor simulation can be achieved using additional finite element analysis data on spatial harmonics to facilitate the development of torque ripple mitigation algorithms and optimized drive design. With the use of Simscape Electrical, we have capabilities to model different levels of fidelity. So now we have an accurate plant model, and we are ready now to design our field-oriented control algorithm. Field-oriented control provides maximum torque per ampere or field weakening control for various motor types, including inductance machines, permanent magnet synchronous machines, and BLDC motors. The block diagram here shows a field-oriented control algorithm that includes the following components: a current controller consisting of two proportional integral gain controller, an outer loop velocity controller, and a current reference generator. Also, we have Clarke Park and inverse Park transforms to convert between stationary and rotating synchronous frames, a space vector modulator to transform the reference voltage commands into pulse width modulation signals that could be applied to the stator windings. We have also protection and auxiliary functions, including the startup and the shutdown logic. And optionally, we can place observers to estimate rotor angular position if we are interested in sensorless control. So when designing a field-oriented control, we get to perform several tasks. For example, we need to develop a controller architecture with two PI controllers for current loop. We need to develop PI controllers for the outer loop speed controller as well. We need, for these controllers, we need to tune the gains of all these controllers to meet the performance requirements. It is also necessary to design a space vector modulator for control the PVM. Also, it is necessary to design an observer algorithm to estimate the rotor position and velocity if we go for sensorless control. It is also necessary to design the maximum torque per ampere or the field weakening control algorithms. We need to implement the computationally efficient version of Park, Clarke, inverse Park transforms. We need to design also fall detection and protection logic. All in all, we need to verify and validate the controller performance across different operating conditions. And finally, it is also necessary to implement the controller in fixed or floating point on microcontroller or to an FPGA. So Clarke and Park transforms are commonly used in field-oriented control of three-phase AC machines. The Clarke transform converts the time domain components of the three-phase system to components in an orthogonal stationary frame. And further on, the Park transform converts the two components of this frame to an orthogonal rotating reference frame. So implementing these two transforms in a consecutive manner, it simplifies the computations by converting the AC current and the voltage waveform into DC signals. By the help of motor control block set, we have the opportunity to design and simulate the motor control algorithms with efficient implementation, computationally efficient implementations of Clarke and Park transformations. And also it is true for inverse Clarke and inverse Park transforms with pre-built off-the-shelf blocks. Space vector modulation is responsible for generating pulse width modulated signals to control the switches of the inverter, which then produces the required modulated voltage to drive the motor at the desired speed or torque. So space vector modulation, also known as space vector pulse width modulation, we can implement these techniques, or we can also use pre-built libraries for motor control applications. So by controlling the switching sequence of the three-phase inverter and the on-time duration of the pulses, any voltage vector with varying magnitude and direction can be described for every PVM period. The objective and the goal of space vector modulation technique is to generate the switching sequences that correspond to the reference voltage vector for every PVM period to achieve a continuously rotating space vector. It takes the reference voltages created by the inverse Park transform and generates the duty cycles to be sent to the PVM driver on the microcontroller. So the PVM driver outputs the required pulse width modulated signals to the three-phase inverter, which then generates the desired three-phase voltages to the motor. So the space vector modulation eliminates the use of an inverse Clarke transformation. It operates on the reference voltage vector to generate appropriate gate signals for the inverter on every PWM period. So this technique basically calculates the on and off gating times based on the reference voltage vector, using the gating times to generate the double hump modulation waveforms, then also using the gating times to generate the appropriate gate pulses for the inverter switches. The nature of the generated modulation wave with a double hump maximizes the utilization of the available DC voltage. We can then apply the generated gate signals to the switches of the three-phase inverter to drive the motor at the desired speed. So in order to use the space vector modulation in Simulink, we can just take the pre-built space vector generator block provided by a motor control block set. So let's see how to design our controller. We'll start with putting together the field-oriented control algorithm. So let's take a look at it. So here at the top level, we can see that we have the speed control loop and the current control for our motor control algorithm. In the speed controller, we will basically computing the IQ reference to track the desired speed. We will use for that conventional PI controller with the anti-windup. We will navigate to the current control now. We can see that if we navigate to this subsystem, we have the sensor processing for the current and the position measurements. In the position measurements, we can also see that how we decode the quadrant encoder readings using the blocks provided by motor control block set. So we moved to the control algorithms in the closed loop field-oriented control, where we have placed the so far discussed Clarke, Park, inverse Clarke, and space vector generator blocks. And inside the current controllers, we are using two PI controllers for the ID and the IQ part. And generally, we can see here how the computed duty cycles are written to the PWM drivers on the microcontroller by these specific blocks. And as we already saw, and it was already shown earlier, we have at the same model the plant model, the physical plant model, so we can run closed loop simulations from here. Now I would like to show you a workflow to how to tune the lobe gains of current and speed controller. So we will use Simulink real-time to automatically tuning the FOC PI controller. Unlike the traditional process to manually tune one loop at a time, which is quite time-consuming, with the FOC auto-tuner block, also provided by motor control block set, we speed up the tuning process by automatically fine-tuning the DQ current axis and speed loop based on specifying the target bandwidth and phase margin on each loop. So we will see an example for that. So this is the experiment setup that we use in a motor control hardware kit provided by SpeedGoat. So the kit includes a SpeedGoat baseline, a real-time target machine with SpeedGoat inverter and motor kit. The motor comes with Hall sensor and encoder. Here, in our case, we will use the encoder signal to find out the rotor position in this experiment. So let's see how the model is set up in Simulink. So we have the speed and current control loop as we have seen before. So it is generally the same. So as we can see, the model, the control algorithms have the conventional PI control for also the current loops and the speed loop. Just as we saw earlier, they come with default PI gains. And the task is to tune these kinds of gains for the three PI controllers. And for that purpose, what we will use is the FOC auto-tuner block. In the FOC autotuner block, we will basically set up the target phase margin and the target bandwidth for both the speed and current loops. Once the autotuner computes the better gains, the gains will be updated, and it is also possible for us to decide when should this update occur in the process. So now we start the simulation. We can see the variation in speed due to the perturbation in the current and speed. So we can also observe the speed response has improved after the tuning. So we can also see here at the display box, it shows the computed PI gain during the simulation. And I also want to point out how we can do fine-tuning on current and speed loop if we have the perturbation. So in order to test it on the SpeedGoat kit, we will now build the model, load the application to the target, and use the commands to start the application on the SpeedGoat target. Again, we can use the data inspector logs the signal from SpeedGoat target. So we can also see here the PI gains that are calculated. And finally, we can basically compare the two simulation results and see the differences between the results and the computed PI gains of the simulation and the target. So with the FOC autotuner workflow, we are able to tune our motor control loops quite easily and quickly. Now that we have verified our control algorithm in desktop simulation, we are ready to deploy it to the embedded microcontroller. If you remember, we are using a TI-C2000 motor control kit, and the code we generate from a motor control block set is a standard C code, which means that we can target to any microcontroller. With the reference examples, we can partition the model so that the FOC algorithm is packaged into separate model, and it is separated from ADC and position sensor measurements and pre-VM writes. So we can automatically generate code, let it be either floating or fixed point code, download the model to the target and test it. So the key point here is that we can generate the algorithmic code that includes the current and speed loop control and integrate this code into our motor control application. We will now see how to deploy the algorithm to TI-C2000 microprocessor. Here's our model. It is exactly the same model we verified before in the simulation. So the sample times colors are turned on. So we can see here the different sampling types. For example, the speed loop basically runs 10 times slower than the current loop. And we can also see the data types on the signal lines. In this case, we will be generating fixed point code. As a next step, we start the code generation process. Both the algorithmic and the driver code will be generated. It is then compiled and downloaded on our processor. And as we can see here in this code generation report, all the generated code is open and accessible to us. We now can open a host model and run the simulation. So in this way, we can basically run our algorithmic code on directly on the hardware. So now we start and turn the motor on. With that, we can implement and test our code directly on the hardware by the provided host model, and we can see the selected signals as well for debugging. We can use a knob or other controls to change the speed reference, and we can see how the speed responds in the scope as well. So we can do a series of tests, including small steps and large steps to test our algorithm on the hardware. And we can also look at different signals of interest, such as phase current reference and phase current feedback. This basically concluded our workflow for motor control design. To highlight it, we have walked through from sensor calibration to plant modeling, up to control design, and finally to implementation. Hopefully these capabilities can help you speed up your development process. Motor control block set expand supported motor references to induction motors and 6-step commutation BLDC motor as well. So it means that we can follow the exact same workflow we just saw on the PMSM machine. By following the pre-built examples and motor blocks, we can quickly run desktop simulation and generate code from them. So at this point, we have arrived to the end of the presentation and to the webinar series as well. I want to thank you for joining into the power electronics control design, and feel free to contact us if you have further questions or if you need support in this or any other topics. Thank you.